All right, so our next speaker is Souparna Nath, and he will tell us about the free energy of the large N fermionic Chern-Simons theory in the temporal gauge on R1 times S2.
Okay, thank you for giving me an opportunity to present here. I'll be talking on fermionic Chern-Simons theory on sphere cross S1 in the temporal gauge. I'll define what temporal means here. So this work is done in collaboration with Professor Sriraj Minwala from TIFR, and this we have a paper on this and also some work in progress. So basically, the objective of this paper, of this talk, is to take a UN vector fermions coupled with Chern-Simons theory, UN Chern-Simons theory, and then compute the free energy at exactly at at large n. But now, why do we want to do that? Because we could also do the same for bosons, UN bosons coupled with Chern-Simons theory, and compute the partition function and the free energy. And turns out they are same. So this is basically a follow-up of a large goal, which is to establish Bose and Fermi duality in 2+1 dimension. So just to give you some background on this, already a Bose-Fermi duality has been established at the level of free energy in flat space, but that is done in light cone gauge. So light cone gauge is basically where you take A1 plus IA2 as A plus and A1 minus IA2 as A minus, and you define one of them to be 0. Now, in order to continue this to any arbitrary manifold, we would prefer light cone gauge is very weird, and it's very hard to compute. So our natural choice for that would be to choose the holonomy direction, which is the temporal part. So which is what is called temporal gauge. Therefore, the first goal is to reproduce the results, which is already established in flat space in the temporal gauge, which is what we did in our first paper. And now we are trying to generalize this on an arbitrary manifold. Like the first case is for the sphere, which I'm presenting here, and the end goal would be to do it for general Riemann manifolds. Yeah. So now one more thing that I want to point out here is why is it interesting to do it case by case on a sphere and then maybe on a torus, is because see, if you consider a sphere and if you consider fermions have Dirac operator, the spectrum of Dirac operator on the sphere, coupled with spin connections because these are fermions, whereas bosons have the spectrum of a Klein-Gordon operator, and somehow they conjure up to give you the same free energy. So we want to understand at the precision level, where is this duality happening? Okay, so this is the path integral of a theory. Basically, this is the Euclidean action of our theory. We have the fermions coupled to Chern-Simons. This is Chern-Simons action, and at this level we can define it on any arbitrary manifold sigma. Later we'll specialize to S2. So yeah, what I mean by the temporal gauge here, ideal temporal gauge would be A3 equals to 0, but that is not possible on any manifold other than this flat space. So basically we choose del 3 of third time derivative of A3 to be 0, which basically implies that the holonomy field is also has a time derivative to be 0. Now this is the choice of the gauge we have for our case. Other two are similar to all previous papers, which is basically to fix the remaining gauges. What you do is you reduce this UN gauge of the A1 and A2 to U1 to the power n by basically demanding that this temporal gauge be that this holonomy field be diagonalized at every point on the manifold sigma. And after U1 to the power n, what remains is to just completely fix the gauge by imposing a Coulomb gauge, that is del I AI equals to 0. Or in other words, we just have mu dot is the spacetime index. We just have A1 and A2 to be following this particular choice of a particular form. So here A is basically the non-trivial circles on a torus, let's say. For sphere, this is irrelevant. Now this looks nasty, but I mean it's sorry. Yeah. So, but just bear with me. So basically, this is our action after reducing to U1 to the power n. What we have is these two terms are from the Faddeev determinant. This is like a flux passing through your manifold. This is the Ricci scalar and the van der Waals. This part is your free determinant, free action, and this part is the interacting term, the 4 form interacting term after integrating out the gauges. This is the generic form you can have for arbitrary manifold. For our specific case to sigma S2, one simplification happens is that this fluxes becomes just numbers. So this is what reduces to become it becomes n alpha here, as you see. And also we'll do a simplification, we'll take large n, where this van der Monde becomes global, and so this integrates out. So this piece is basically becomes irrelevant. That is why we do large n and large and in S2. With all of this manipulation, what remains is this basically this effective action. Note that because of this particular choice of e to the power I n alpha summation n alpha lambda alpha, this is like a Dirac cone. So it basically quantize lambda alpha the eigenvalues of the A3. So they are the holonomies, and they quantize as the holonomy. So this wouldn't have happened had we not taken large n. So anyway, at the end of the day, this is the effective action we are left to calculate. So we start with the free part, and the free part is basically a normal Dirac operator, except that we have spin connections because we are doing fermions on a sphere now. Mu is just normal your gauge field. So now I'll show what the spectrum of this is. But just for some intuition, had it been scalars, we know natural basis on a sphere is spherical harmonics. Turns out this is, and since this is flux flux lines passing through S2, this is exactly that, except that now you have monopole weighted spherical harmonics. So basically there are some special type of spherical harmonics which are like this. So these are the eigenstates of a Dirac operator on a sphere. There are two components, one for the spin up, one for the spin down. You have normal Jm as in angular momentum J of Ylm, except they are also weighted by the monopole charge, the flux charge. And going back 2 slides, these are some few properties you can just go through. One of the interesting properties is that the angular momentum now, instead of starting from 0, starts from the flux charge S. Similarly, also another property which we needed mostly was the fact that for the same monopole charge, the orthonormal relation obeys. And with this, basically with this we have this action, and with our action and this Dirac operator spectrum on our hand, we just plug it back and we do a Schwinger-Dyson procedure, which gives us this gap equation. So if you look, this is the gap, this is the quantity we need to compute, and this is also inside the summation, or if you want inside an integral. So this is an integral equation. If you guys are familiar with diagrams, then this is basically this diagram. So these are what you call rainbow diagrams. So effectively what you do is, in this blob it can be anything. So you just keep on adding this plus 2 loops like this plus many loops like this, and then you compute this. And that is what, so this is the reason why we are calling it as exact, because we could exactly solve this. So it's like the sum of all 1PIs you could have. And now this is what was there in a previous paper, which and you see the similar analogy. Is exactly similar, except the fact that you have this summation over J replaced by integral. So basically, this is what you expect, because on a sphere now, even your space direction have quantized into just momenta. And rest of the stuff are pretty explained. So H is just something, just this particular choice is gamma 1 matrix gamma 2 minus the antisymmetric combination of that. So technically, what at the end of the punchline is we have to solve this for sigma, and yeah, these are the solutions we have. So this is our gap, which is given in terms of this momenta, and also something called omega. Omega is a weird function like this. In flat space case, these all could be exactly evaluated. I'll show just one slide later. But in a sphere case, we are yet to actually work out if there is some analytic forms, or then if not, then we'll try to do some perturbator around the thermal mass. Let me give some explanation for you. R is the radius of the sphere here. Beta is temperature, inverse temperature. Q sigma are the fluxes, and mt is the thermal mass. So if you see here, what happens is at the end of the day you get this equation. So this says that thermal mass is basically bare mass shifted from some coupled equation which depends on thermal mass. So basically, even if you start with 0 mass, a bare mass theory, at finite temperature you generate some mass, which is basically saying that this is a finite temperature theory, and you generate a mass because of dynamical generation of mass. So plugging this all of this into the free energy, into the action will give us the free energy. For the flat space case, this is what we had. We had some exact analytic form for this, and this was also the form, as I said, for the flat space case. For sphere, we are yet to find out if there is some analytic form for this. Other than that, one more result which I would like to say is this is the quantity, this is the shift in mass of the self energy. Turns out that for the flat space case, this was this green line, and for the sphere, it is this red line, which happens to be, we do not know for sure, but which seems like it's always below the green line, suggesting that this may be a vague idea. That so this plot is basically mass versus this correction. So as you keep on increasing the bare mass, it seems there is an overlap between the flat space case and the sphere. We have an intuition in the sense that, yeah, I'll be done. We have an intuition in the sense that, just from naive de Broglie analysis, de Broglie wavelength analysis, for a massive particle, it is a massive particle has a very localized de Broglie wavelength, so therefore it cannot distinguish a sphere, the whole of a sphere, from a flat plane, because a sphere looks locally flat. On the other hand, if you have low masses here, then actually it's like a huge de Broglie wavelength, and so it's covered the entire space. So it can distinguish a particle kept at rest on a sphere can distinguish a sphere from a flat space case, and that is why we are suspecting it's showing a difference. Now, why is it below the flat space case? We do not know. Also, there are some other things which we have recently observed, but I have not mentioned here. One of them is that in the flat space case there was no flux. Here we have flux, and there's a severe dependence on fluxes, in the sense that one of the recent results we have seen is that for certain fluxes, so this is basically, this blue line is basically, where the blue line cuts this green line, is where the final, so this is the line y equals to mt, and this is the curve, this thing. So wherever they match is where the solution, where the final mass you have. Turns out, for different holonomies, you can tune the holonomies such, you can tune the fluxes such that this red curve never intersects with this blue curve, so and you have no solutions. So this is something puzzling which we want to understand, that why are there certain fluxes beyond which it's like plugging in a magnetic field will give you no solution to this Bose-Fermi duality. And also, yeah, at finite volume we have some, this is what I was talking about, that at finite volume we have this number of determinant term contributing from different sectors. So it's like the mass we are having here. If you see phi t, just a moment. Yeah, okay, if you see phi of t, there was no flux in the flat space case, but if you see phi of t here, there are flux dependencies. So basically we have to sum flux by flux sectors. Therefore we want to understand that. Also, something which will be very interesting is to, if possible, to compute some S matrix, do some S matrix analysis for this choice of temporal gauge, and if you can see if there's if it sheds some new light on this, crossing symmetries properties. Finally, the reason I started with claiming Bose-Fermi duality, but I never presented here the bosons part, is because we are still troubled with a coupling constant called phi square a square for the bosonic. This gives rise to an infinite series of diagrams. Somehow they all must sum to some trivial number. So otherwise it's almost similar. So had that been the case, we could have actually shown that the Bose-Fermi duality works out even for sphere. But yeah, so these are my future iterations, and these are my references for this. Thank you.
Thank you very much. Are there any questions?
So you said that for some fluxes the curve doesn't intersect the blue line. So what happens to the curve? Does it shift to one side of the line?
It shifts to the negative.
Okay, so the y-intercept becomes negative, right?
Become negative, yeah.
Okay, is that unphysical?
That because I mean that's not I won't say it's unphysical, but it's surprising in the sense that there exist sectors where you have no set. So no intersection would mean that the theory doesn't exist. So it's like there's no mass. You cannot have a theory which generates or negative mass.
Right.
So
yeah, I mean, no intersection will definitely say that the theory doesn't exist. But what I'm asking is that having a negative y-intercept, is that unphysical?
Is that unphysical? No, in this graph it won't be unphysical, because this is that's not negative mass. That's basically saying that bare mass minus this thing is negative.
Okay, I see. Okay, thanks.
Any more questions? All right. If not, let's thank Souparna again.